So today we have Alessandro talking about SymTFT in Superspace.
Thank you very much for the opportunity you've given to me of speaking of this latest work that, let's say, is the start of a project about studying generalized symmetries in the context of supersymmetric theories, and which is let's say, a topic which is not that investigated. So in this talk, I'll give the presentation of this work in collaboration with Federico Ambrosino, Pietro Antonio Grassi, and Silvio Penati, who is my supervisor in the University of Milano Bicocca, where I'm a PhD student. And basically, it's just a proposal for a symmetry topological field theory in superspace. So let's get started by giving an introduction and some motivation for this work. Well, we all know that symmetries have always played a fundamental role in physics, and in particular in QFT. They are the foundation of QFT, as, for example, they do imply word identities between correlation functions, which are then, let's say, constrained by these identities. They might also give information about the strong coupling regime of a theory, which is usually difficult to tame, to understand. And for example, tooth anomaly matching of symmetries can help us understand some of the couplings in the strong coupling regime and all that. And we know, obviously, that symmetries also help organize observables and quantum number of systems into group representation and so on. So the idea of studying symmetries is obviously a fundamental one in theoretical physics. So what we also know for a decade or so, at least now, is that we can enlarge our perspective on symmetries by what are now called generalized symmetries, which is a way of look at symmetries in terms of topological defects. And we will review this idea afterwards in the presentation. So, based on this idea, where now symmetries are related to topological defects, there exists a systematic approach to study generalized symmetries in the context of studying topological defects, and that is the study of symmetry topological field theory, which I'll explain in details afterwards. And we know that this approach is well established for global and finite symmetries, but it was also recently extended to continuous and spacetime symmetries. So the idea is, let's say, fairly simple. We know that supersymmetric models are a vastly studied topic in theoretical physics, and trying to include them in this framework on the SymTFT in let's say, manifestly supersymmetric fashion is exactly what we wanted to do with this work, and was exactly the goal of this project, and hopefully many others that has yet to come. So this is, let's say, the ground state that we want to build from it. And the plan of the talk, we go this way. I'll give, let's say, brief introduction to the notion of generalized symmetries, and then explain what is the symmetry topological field theory. Then I'll introduce you to some tools of supergeometry, which is the language that we use in order to develop our SymTFT in superspace. And it is useful in order to describe the core of our proposal, which are super-BF theories, which are supersymmetric topological field theories that we will use in order to define our proposal for a SymTFT in superspace. And then I'll obviously explain what we built, which is the SymTFT in superspace. And after explaining the proposal, I'll give an example that we studied in this work for the supersymmetry TFT for the 2D supercompact boson theory. And after that, I'll give an hint at the possible future direction that may come from this work. So, okay, now let's get started and enter the meat of the project. So it's been like more than a decade now that from the original work of Gaiotto, Kapustin, and Cyber-Willett, we know that generalized symmetries, that symmetries can be understood in terms of topological defects and in what is called the framework for generalized symmetries. In particular, we know that we have a p-form symmetry in a QFT when there exists a codimension p+1 topological defect, which I'll call in this talk UG of sigma, where sigma in this notation just labels the codimension p+1 supporting surface, and the fact that the defect is topological means that it is independent under the continuous deformation of such surface. And G instead just labels what I'll call generically the symmetry element. We know that in the context of generalized symmetries, the underlying mathematical structure that describes the symmetry can go well beyond that of the group, which we are, let's say, used to understand as the structure of a symmetry. And indeed, they're described by more like algebraic fusion algebra of operators, or just maybe more categorical structures. And let's say that G just represents an element inside these underlying mathematical structures that is dubbed to be invertible if it's related to a group-like structure, or non-invertible if it's related to a more abstract algebraic or categorical structure which has non-invertible elements. So, okay, these are the notation of the topological defect that implements a symmetry. And in this new language, what we used to understand as a symmetry are just invertible zero-form symmetries. So we know that in this language, we have a much more richer structure of symmetries for a QFT. So an example of this higher form symmetries, let's say, is that of the U1 electric times U1 magnetic one-form symmetry in 4D Maxwell theory. And in particular, indeed, in 4D Maxwell theory, which is the theory of a massless gauge field, A, with the field strength F, we have that we can build two topological operators, which are two-dimensional. Indeed, these in the blue box are the topological operator related to the U1 electric and U1 magnetic one-form symmetry. And they are the exponential of the fluxes of F and star F, which are obviously related to the field strength of Maxwell theory. And given the fact that for the equation of motion, the star F and for Bianchi identity, the F are zero, we can then prove, obviously, that these two operators are topological. So what exactly does it mean that these two operators, or in general, a topological operator implements a symmetry? Well, it actually means that there exist charge objects under such p-form symmetry, and such objects are p-dimensional extended operators. So let's now try to understand how these operators, this topological defect acts on these extended operators. And let's call this p-dimensional operator O of gamma, where gamma is the p-dimensional surface where the operator is supported on. We can look at the picture here, and let's imagine that we have a codimension p+1 topological operator, which is this blue line that encircles these extended operator. And we can imagine, being topological, to shrink it down to the intersection point between these two topological operators, these two operators, the topological one and the charged one. And what happens is that by shrinking, word identities implies that there's the action of a certain representation of the symmetry element G related to the topological defect, exponentiated by this linking number between the surface sigma and the surface gamma. So this is the action of the topological operator onto this charge extended operator. And let's start understand what the linking number is. And in order to be precise, let's imagine to fill this topological operator by this light blue surface. And let's count how many oriented intersections there are between this extended p-dimensional operator, which is the charge one, with this surface that fills the topological operator. And when we count these oriented intersections, we are exactly counting this linking number, and it's actually just a topological, well-defined topological quantity that says that the two operators are linked amongst themselves. So this is actually what happens in the context of generalized symmetries when there is a symmetry. It means that there is a topological defect that acts on a charge one, and so that the dimension have to match in order to so that the sum has to be d plus one. Yes, d. Sorry. So this is standard law of generalized symmetries, and there's a way to understand, like a systematic way, in order to understand this relation between topological defects and charge objects. But let's first see an example of these charge objects, as we've seen an example of the topological operators. And I'll do the example of the charge object in the 4D Maxwell theory. These objects, indeed, we know that there is a one-form symmetry in 4D Maxwell theory, and there exists one-dimensional extended operators, which are Wilson lines, and such Wilson lines are indeed charged under the U1 electric one-form symmetry that I described before. And this operator acts on the Wilson line by a U1 phase. This is actually what it means that it is a U1 one-form symmetry. Okay, so this is basically an example of these diaform symmetries in the context of 4D Maxwell theory. Basically, this is the standard law. So there's a systematic approach in order to investigate the relation between charge defects and topological symmetry defects, and it is that of the symmetry topological field theory. And now let's explain how this works in practice. So let's imagine now that we have a theory living on this blue d-dimensional manifold MD. Okay, so we have a theory that lives in the dimension. And what we want to do is that we want to extend this manifold by a compact interval and build this d plus one dimensional manifold with two boundaries. And we have to basically define a topological quantum field theory that lives in the bulk. And then we have to fix the boundary conditions of this topological quantum field theory that lives in this construction, which is usually called the sandwich construction or the slab configuration. So what we have to do is that we have to at the physical boundary, which is this blue boundary, we couple the physical theory that we want to study to the background gauge fields for the symmetries in question. So basically, we just couple the currents in the case of continuous higher form symmetries, we couple the currents to these background gauge fields. And then what we do is that we extend these gauge fields into the bulk to be dynamical and to be the gauge fields of this topological quantum field theory, which lives in the bulk and which has non-trivial observables. Like usually the most notable examples of this topological quantum field theory are BF theories. And indeed, our next proposal in the supersymmetric case is based on SymTFTs, which have BF theories. But in general, this is a generic TQFT. And on the other side, we have to fix the topological boundary condition, which means choosing what is called a Lagrangian subalgebra of operators or that lives in the bulk, and this Lagrangian subalgebra of operators means choosing a maximum set of mutually commuting operators on the boundary. So by doing so, we are basically choosing which operator can end on the boundaries, and basically upon squishing this construction into as the theory between the two boundaries is defined on a topological interval, we can squeeze this interval, and what happens is that these operators that live in the Lagrangian subalgebra upon compactification of these constructions become the charged defects in the theory, while the other operators, these green ones, are basically the symmetry operators that implement the global symmetry at the physical boundary. So there's basically a way to decouple the dynamics of the theory that lives in a physical boundary to the symmetry structure of the charged objects and the symmetry defects, and to study it systematically inside of this topological quantum field theory, which has these topological operators that braid non-trivially. We will understand this in example that we studied in our work. So this is the standard law to understand what is the symmetry topological field theory. And now I'll give you some tools of supergeometry which are helpful in order to uplift this construction to the supersymmetric case. So the idea is that as the most natural language in order to describe these higher form symmetries is that of differential geometry in the use of forms, of gauge fields, and all that. Well, the idea is that what we want to do is to define this in the context of supergeometry, which will be the most natural language in order to study supersymmetric theories. Okay, so let's start by a not so rigorous definition of a supermanifold, which will be helpful in order to just understand, let's say, heuristically how the geometry of supermanifold is. So let's say that a supermanifold with dimension nm is a non-commutative geometrical structure which locally looks like superspace. What does it mean? It means that it is described locally by coordinates that are both bosonic and fermionic. So we have these n bosonic fermionic dimensions and these m fermionic dimensions, which are anti-commuting Grassmann variables. So this is just what the supermanifold is. And given these coordinates, what one can do is build all the geometry machinery on it. So one can build the tangent bundle. So at each point in this supermanifold, one can assign the vector space of of the derivatives, which are both bosonic and fermionic. Okay, so these are the definition of the bosonic and fermionic derivatives. So this is actually the tangent space at each point. And then one can be also the dual cotangent bundle, which is spanned by this super differential, which are indeed supersymmetric invariant differentials, which are called V and psi. And they actually have the opposite statistic of their coordinate counterparts. So obviously we know that under the wedge product, the bosonic differential are antisymmetric, while the fermionic ones indeed are symmetric under the wedge product. So, and we will see that this will give rise to a much richer structure in supermanifolds for differential forms. And then given these ingredients, what one can do is build the super differential operator, which is just a supersymmetric version of the RAM differential, which squares to zero. This is the definition of it. And why this language is useful? Well, the language of supermanifold basically can capture supersymmetry very well in terms of a space-time symmetry. Indeed, as we know, in this language, supersymmetry is given by a differential operator, which is just basically we can understand it as a fermionic translation. So basically, the adding of these fermionic directions is helpful in order to capture supersymmetry in terms of a space-time symmetry, which does not commute with the useful with the standard, let's say, bosonic space-time symmetry. So this is basically the setup of a supermanifold and its geometry. These are the geometrical objects that we will use in order to define what are super differential forms. And the general structure of a super differential form is given by this expression. We can see that there is a super function, which is a function of both bosonic and fermionic variables. And I've suppressed the indices of this super function, which are contracted with these super differentials that we just introduced, both the bosonic and the fermionic. But we also see here this delta of size, which are basically a new object, which are called pictures. And these objects are basically distributional Dirac deltas with respect to these differentials, and they are needed in order to define a consistent integration theory of these super differential forms. So given these objects, one can indeed build an integration theory of differential forms as they do satisfy the antisymmetry property. So obviously one can build top forms given the fact that these two objects are antisymmetric, and they do satisfy these Dirac delta properties. And in particular, we can have derivatives of these Dirac deltas, and such derivatives act distributionally on these differentials, and basically eat these fermionic differentials and lower the degree of the differential form. So now a super differential form is given by two numbers. One is the usual degree of differential form, and now we have this new object, which is the picture. It's the picture number that counts basically how many Dirac deltas there are. And then there's the degree, which is basically the number of the super differential in the form expansions, minus the number of derivatives of these pictures, which, as we've said, lower the degree. So this is the much more richer structure of superdifferential forms. And indeed, what we have is that we have differential operators that helps us moving between the space of these differential forms. In particular, we have the superdifferential, which basically moves up the degree by one, and then we have these derivatives, both the usual. This is the usual differential. Oh, sorry, what happened? Okay, sorry. Okay, this is the contraction, which basically lowers the degree. And in the fermionic sense, these are the Dirac delta derivatives that we've just described. So we have these two operators that allow us to change the degree of a form. But now what we also have is that we have picture changing operators, which are these y's and z that I do not describe in details, but let's just say that there exist these differential operators which help us moving between the space in the space of superforms, and they basically add or subtract the picture inside of these forms. So they allow basically to change the picture number of a form. And these objects, Y and Z, are closed but not exact objects, and so they are maps between cohomology classes of different pictures. So what is the general web of these manifolds? Oh, sorry, of this. Let's say there's something wrong with. Okay. What is the general web of differential forms in supergeometry? Well, we have superforms, which are forms with no pictures. And given the fact that these fermionic differential are commuting, we can stack them an arbitrary number of them, so there is no maximal degree of these superforms. So we have a complex which continuously grow in the degree. Then we have on the opposite side integral forms, which have the maximal number of pictures, and so there are all the Dirac deltas present. So there is no room for the psi's as they are killed by these Dirac deltas. And so what we have is that we can have a top degree n, but as these Dirac deltas allow for derivatives, we can use these derivatives to lower the degree. And as the fermionic derivatives are commuting, what we can do is that we can go back infinitely in the degree. So there is no lower degree for these integral forms. And then we have pseudoforms, which are let's say, middle ground between these two superforms and integral forms, which have a Q, which is between 0 and the maximal fermionic dimension. And so they can have both this size and also arbitrary derivatives of these pictures, and this gives a complex which is unbounded from above and below. And what one can do is use PCOs, which are picture changing operators, to move between these complexes between superforms, integral forms, and pseudoforms by lowering and raising the picture number. So this is basically the whole structure of super differential forms, and why I describe this whole geometrical machinery of differential forms. Well, because they are, they are basically the building blocks of studying super higher form symmetries. In a recent work last year, Antonio Grassi and Silvio Penati, which are collaborators in this work, developed what are continuous super higher form symmetries. As we know indeed that in the bosonic case, when we have a continuous higher form symmetry, we have a conserved a conserved current, which is related to this closed d minus p minus 1 form, and we can integrate this d minus p minus 1 form onto this manifold and build a topological charge, which is the symmetry charge Q, and this topological quantity can be exponentiated, and this gives rise to the topological operator that implements the symmetry, as we've seen before. So basically, the language of differential form is the most natural language in order to describe continuous higher form symmetries. In order to define all these topological defects related to these higher form symmetries. What one can do is use the language of PQ forms in order to define PQ form symmetries, which are manifestly supersymmetric, meaning that the topological operators that implement these super higher form symmetries are supersymmetric. So we have these closed superforms, which obviously, given the closure, one can integrate them, given the presence of these pictures, one can integrate them and build this topological charge at the same level of what we did in the bosonic case, and we can take this charge and exponentiate it and basically build a manifestly supersymmetric analog of these topological operators that implement the symmetry. And this machinery is well studied by Silvia and Antonio in this paper where they studied this super higher form symmetry in the context of super Maxwell theory. Why it's also useful to study supergeometry? Well, the idea is that
Sorry, could I just ask a question about the previous slide?
yeah, obviously. Okay, sorry, there's something wrong with the. Okay, yeah.
Oh yeah. So when you have Q as 0, you should be able to recover the non-SUSY case, right?
Yeah,
they should be
that's true.
equivalent.
Yeah,
Okay.
that's true. That's true. Because the fact is that basically, okay, the idea is that when you do a non-supersymmetric theory, you don't need to use supermanifolds, so you don't need to have all these extra fermionic dimensions. But what you can do is that you can see that obviously these forms match into these forms when there is no picture. So.
I see.
Yeah. Indeed,
I was just wondering, how would you get rid of the fermionic dimensions? So, like when
well,
Q is 0, you have M, right?
Yeah. Okay. Yeah. Basically, it's that this M is just an embedding of this bosonic manifold inside of this supermanifold. Yeah, it just let's say that inside, if there is no like interesting fermionic structure inside of this form, there's this M basically just represent a way to embed this form which lives just on the bosonic manifold into the supermanifold. So I don't know if you're familiar with the concept of the Poincaré duality. So there is this Poincaré dual form, which basically embeds everything inside the supermanifold. So this is
I see.
this is the idea.
One other quick question on slide 12.
Slide 12. Okay.
Yeah. I was just wondering why the sequence didn't terminate in terms of the superforms. Is it because there's M degrees of fermionic dimensions still, like implicitly?
Yeah, that's true. That's true. But the fact is that, okay, as we've seen here, where it is here, okay, the degree is given roughly, okay, let's by counting how many super differential there are, both bosonic and fermionic. But we know that the fermionic ones are commuting with respect to the weight products. So I can have an arbitrary number of them, okay? So the degree here can grow with S, which is the number of these fermionic ones, can grow as we want. While in the case of just bosonic, R can be at maximum the n dimension, because we know that these are anti-symmetric. So if we add an n plus 1, it has to be one of the other ones. So by anti-symmetry, it has to be 0. Okay. I don't know if I explained
I think
myself.
I get the idea.
Okay.
So the
Okay.
anti-commuting one's going to
As there
terminate.
is no direct deltas, there are just these basically these fermionic differentials, and I can stack a lot of them arbitrarily. So the degree can grow whatever. Okay. While when we have pictures, some of the if we have all the pictures, these are killed basically by the pictures. Okay, so we basically can define an integration theory. Okay.
I see. Yeah, that makes sense. Thank you.
Okay, no problem. Any other questions? Okay, so let's go on by describing what super BF theories are, which in the language of supergeometry basically come from uplifting BF theories, in the case from manifolds to supermanifolds and from forms to superforms. So now we have BF theory, which is given by the usual action, but now it's defined on a supermanifold with superforms B and A. So what happens is that we can define topological field theories, which are given by a theory of flat connections. And this topological theory is basically the building block of our SymTFT proposal. And given this flat connection, one can build indeed the topological operator inside of the BF theory, which are useful in order to understand the braiding relation between the charge objects and the symmetry objects. Okay, so I'll give you a brief example of a super BF on a 3/2 supermanifold, which is given by these two forms, B and B tilde. And what we can do is we can build the field strength of this B tilde, which upon conventional constraints, I don't want to enter these technicalities, is given by these two expressions, which are superfields that capture the bosonic field strengths and the gaugino, basically. So we can do that also for the B field. In order to describe the B field, we define an auxiliary Matkal B 10 form. And what we can do is that given the same analogous field expression, one can basically build the B in this way. So it has this Matkal B and this gaugino, which is exactly the super partner of this B field strength, times a picture changing operator, which basically defines the exact dimension which is correct to match the superform picture number. Okay, so given these two elements, one can wedge them between themselves and obtain this expression. And upon integrating on a supermanifold, we obtain what is known to be a supersymmetric BF theory, which has B as gauge fields and lambda as the gauginos, which are partners of this B and B tildes. Okay, so we've seen that we can basically describe a BF theory in the geometric language using supergeometry. Okay, so given that, now I'll explain what exactly the SymTFT is. So I'll have to go a little bit fast, but it's okay. What we do is just we want to uplift the description that I had before of this lab configuration by basically taking a supermanifold instead of a manifold, and basically build this lab configuration using boundary supermanifolds that now we have to be careful about the fermionic dimension. So basically, we start with a bulk supermanifold, which has to have the double of the fermionic dimension. Why? We know that in order to preserve SUSY on the boundaries, boundaries break SUSY in half at least. At maximum, what one can have is that on the boundary, only half of the SUSY is preserved. So what one has to do is that the boundary that lives at the SymTFT has to have half of the fermionic dimensions of the whole bulk construction. So the SymTFT in this case is given by a supermanifold which has one more bosonic dimension and twice of the fermionic ones. Basically, this is the idea, and these two boundaries are connected by this super interval, which basically carries these extra 1 and m dimensions. So what everything else basically follows neatly. Basically, if we have a theory which is defined in, let's say, supergeometric fashion on the boundary, what one can do is now couple it to gauge fields, which are now superforms or integral forms. And these integral forms become basically the gauge field of the super-BF theory, which now lives, that we've just described, which now lives in the bulk. Okay, so we have this topological quantum field theory, which is supersymmetric, which is given by this super-BF theory, which lives on the bulk. And now we have to fix the topological boundary condition, or meaning choosing a Lagrangian subalgebra of the operators that basically restores the relation between the charge operators and the topological symmetry operators. Okay, so everything else basically follows neatly by just uplifting manifolds to supermanifolds and forms to superforms. But there's this idea which is crucial, which is about halving the fermionic dimensions. Okay, so this is the idea of the SymTFT in superspace, and I'll give you a concrete description of the SymTFT for the supercompact boson. So, what is the supercompact boson? Well, the supercompact boson is a theory which is defined which we defined on superspace. So we used a supermanifold with a flat supermanifold with these like coordinates, z and z bar, and theta bar. And when these all, let's say, these are all technicalities about the vector fields and the supersymmetric differentials and supersymmetry. Okay, so this is exactly the language applied to this let's say, flat supermanifold. And using this language, one can describe a theory for a supercompact boson, which is captured by a scalar multiplet into the flat space. And this is the phi scalar multiplet. And if we want to look at its expansion, we have a periodic scalar field, which basically is defined up to a periodic 2 pi r. And then we have the fermionic superpartners, which are Majorana file spinors in 2 dimensions, obviously. And then we have an auxiliary F scalar field. What happens is that one can define supergeometrically the action of the supercompact boson as this action here, basically using the super differential and the Hodge super operator, which was introduced by Antonio and his collaborators in his work in supergeometry. And so basically one can build the theory of a supercompact boson as the theory of this scalar multiplet on this flat supermanifold. And going in the components of superspace, one can see that indeed we can recover the superconformal field theory of this supercompact boson. So this is the theory, and what what we have is that we have U100 times U102 currents, which are given by the equation of motion and by Bianchi identity. So we have these two conserved objects, and using these conserved objects, one can build the topological defects of the theory, which are the exponentiation of these currents, as we've seen before. And here we're just defining the integration by embedding with these Poincaré dual forms inside of the whole supermanifold. And then we also have the charge operators, which are basically these. They're called vertex operators. Okay. So this is basically the structure of the symmetry of the theory, and the SymTFT. We also analyzed the space-time symmetries, in particularly also supertranslation, but then we didn't study the SymTFT, but we did it as a preliminary work. So we identified these currents, which are the currents that basically, when we exponentiate them using these super parameters, we can recover basically the translation and the supersymmetry currents. Okay, so we identified the space-time currents and the topological defects that implement the space-time symmetries. Okay, so now we're ready to define the supersymmetry TFT, and the bulk QFT is given by an n equal to super-BF theory in 3 dimensions. Indeed, we know that the fermionic dimension have to be the double the dimension of the boundary, which was 2-dimensional in the fermionic dimensions. So we have to have an n equal to BF theory, which is described by this theory by superforms A1 and A2, which are R-valued superforms. Given this R times R symmetry, what one does is that it builds the topological operators given by the holonomies of these A1 and A2 operators, and they have charges which belong, to the. Let's see if it belong to the R field. Okay, so what one can compute is the braiding relation between these U and V's, and indeed what one can see is that they commute non-trivially, and they have this phase which basically captures the fact that U and V are charged among themselves inside of the super-BF theory, and this is the braiding phase, which is proportional to the superlinking number, which is let's say just a generalization to supermanifolds of the topological linking number that we defined before. So this is the braiding of these such operators, and then at the physical boundary, what we do is that we couple the theory to these background gauge fields, and this coupling, if we try to gauge, to promote these gauge fields to have gauge transformation, we see that there is a mixed Tooth anomaly, as in the bosonic case, and this anomaly is exactly captured by the inflow of the BF theory upon choosing this boundary condition. And what one has to be careful about is to match exactly also the picture number at the boundary. So we know that A1 has to be a 1-4 form, but B is a 1-2 form. So in order to match the picture, one has to multiply by the rightful picture changing operator in order to match exactly the forms at the boundary. And upon this identification, what happens is that this anomaly is cancelled. So basically what happens is that then at the topological boundary, we have to choose the right Lagrangian subalgebra in order to recover the symmetry structure that we've seen before. And this Lagrangian subalgebra is given by choosing integer charge topological operators on the boundary. And these operators, upon compactification, become the vertex operators that we've described before. And the other operators realize the U1 global symmetry of the theory that we described before. Other choices of Lagrangian subalgebra could define a different theory. For example, a non-compact theory with an R-shift symmetry would be given by this choice. So this is basically the idea, and I'll end. Okay, now perfect. I'll end with the possible future direction and outlooks of this proposal and this project, because this is just, let's say, the ground that we laid in order to start this study of generalized symmetry in the context of supersymmetric theories. So we've constructed this general framework in order to study higher form symmetry with the presence of supersymmetry, but yet we have a lot of things to do. In particular, we know that the SymTFT was what we studied was the SymTFT for the global symmetries, but the SymTFT framework was recently, as I said, extended to also space-time symmetries. And so a natural direction is to include and define a SymTFT also for space-time symmetries that include supersymmetry. So this is the next idea, and basically one of the reasons because this SymTFT framework in Superspace was developed. And we know that the proposal is fully general, but we only tested for this 2D example. So it will be interesting to see what happens in higher dimensional theories and maybe also theory with extended supersymmetries, and see what happens in these topological BF theories with much more richer structure. And eventually, we hope that this framework can be helpful also to study also non-invertible symmetries in the context of supersymmetric theories. So basically, these are the possible future direction that we will take. And with this, I end my talk. So I'll thank you everyone for listening.
Great. Thank you very much. It was very nice.
Thank you.
I guess people are welcome to ask questions. Maybe could you comment more on what exactly these picture changing operators are? Because I've seen them occur before, but I don't really understand what they mean.
Okay, let's go back. Okay, basically, okay, let's see. In some ways, the picture lowering operators are quite difficult to explain without being technical. But these picture raising operators, we can understand this by a generalization to the fermionic directions of these Poincaré dual forms. Basically, they embed the forms into the higher structure, adding these pictures. Basically, these Dirac deltas are just the exact fermionic analog of the Poincaré duals, which let's say basically the Poincaré dual says that the integral localizes on a certain submanifold, and these picture changing operators allow to define an integral on the whole supermanifold, and these picture changing operators are basically dual to a submanifold, and with lower fermionic dimensions. So basically, it's just let's say localization of this object into this lower dimensional lower dimensional manifold. But okay, they are born in string theory because they are basically needed, but it's a totally different context, but they are the same thing. And they were born in string theory in order to basically gauge fix the supersymmetry, the supersymmetry of the worldsheet. Okay, but they can be interpreted also in this in this fashion into this geometric language. That's I hope to be clear.
When you say that they're used for like gauge fixing, are they related to like ghosts or something or
Yeah.
okay.
They're exactly ghosts. Yeah.
Okay. Yeah.
Yeah. They're actually related to that.
Okay.
And
Okay.
yeah, indeed, what happens is that when you add these pictures into the forms having these pictures also have a redundancy given by, let's say, now we can understand by gauge transformation. Well, when I add a picture, I also have this new gauge transformation for these forms. So basically, we can see exactly that pictures are related to a redundancy, which is given by indeed the gauge fixing.
Okay. Thank you. Thank you.
Problem.